Hi everyone. First, thank you for your time, and for being patient of watching this my first unsupervised presentation. Thank you Dr. Becerra, for your teaching in this course, which has been of great value for me, and hopefully, I will apply what I had learned here in my professional life. Let's start with this work, my study of the precipitation characteristics of the Greater Antilles. The geographic setting of Greater Antilles, in the west part of the Caribbean Sea, and in the middle of the tropical cyclone corridor, exposes them to a great volume of humidity, carried over by the air masses moving from the East Atlantic to North America. This study compares the characteristic of precipitation, in the Greater Antilles Islands, and tries to find the causes of its variations, regardless of their relatively small area, and their position in the middle of the tropical cyclone corridor. The Greater Antilles are the islands of biggest size in Caribbean Sea. It appears in the west part of that region, aligned and disposed from east to west. These are the island known as Puerto Rico, La Hispaniola, Cuba, and Jamaica. The Greater Antilles are located between the 23 and 17 degrees latitude north and the 85 and 65 degrees longitude west. With a total area, for all four islands of about 240,000 square kilometers, it receives an average precipitation rate of 970 millimeters a year. The relief is mountainous in all islands, with peaks at 1,972 meters in Cuba, 3,087 meters in La Hispaniola, 2,256 meters in Jamaica, and 1,150 meters in Puerto Rico. The vegetation is ranging from tropical rainforest in limited areas, to small prairies, and semi-arid regions. The land is used mostly for agriculture, however in some places, it has been transitioning to suburban areas and shrub type of vegetation. Let us start this study with Puerto Rico, the easternmost of this group of islands. Here we have a digital terrain model, depicting the central range and runoff patterns. As we can see here, the highest elevations are disposed west to east approximately, surrounded by the coastal plains, irrigated by the short streams running radially, from the elevations in the center to the coast. The average peak in the central range is around 600 meters. Distribution of temperatures in the island. As a complementary information we have this average isotherm map, courtesy of Daly et al. 2003. Where we can appreciate the isotherms varying upwards, and mapping the elevation features of the relief. Also, is notable that the variation occurs in few Celsius degrees. The average variation with the height is just around 3 Celsius degrees only. The only exception is the area south of San Juan, where a significant part of the mountains does not correlates well with the isotherms. Here we have the yearly average rainfall rate, after Daly et al. 2003. Coincidentally with the temperature map, it also shows a great correlation with the hypsometry. It can be seen in the east tip of the island, around the top of the Yunque, is where the highest volume of rainfalls occurs, more than 4,000 millimeters a year. While in the rest of the territory, there are a great variation from less than 1,000 millimeters a year, to 3,000 millimeters a year. However, we notice that, the same area, South San Juan to southern coast, there also is an exception in the correlation between ISO heights and elevation. The vegetation coverage was obtained by computing the layer provided by MODIS V6. Here we can appreciate the density of vegetation and the land use of Puerto Rico. Again, we can appreciate, in general terms, the correlation between the elevation factor and the vegetation. However, here this correlation is weaker than the correlation between ISO heights and vegetation, which is a clear direct relation of the land use to the precipitation rate. It can be noticed that the denser vegetation occurs where the highest rate of rainfall occurs, and the areas with less precipitation are those with less vegetation density, even deforestation. Here we have a bird's-eye picture of a major section of Puerto Rico, including the area of exception in the correlation. As can be appreciated, the deforestation of flat and low slope area of the island corresponds with we have seen in the previous vegetation density maps. Perhaps this has much to do with the scarcity and distribution of precipitation and water resources in general. The digital terrain model for La Hispaniola, depicting the 5 ranges and the basin in between. La Hispaniola features 4 parallel ranges disposed southeast to northwest, and 3 valleys in between. The 5th range appears in the east side of the island and is not as high as the previous 5. Average ISO heights in both Haiti and the Dominican Republic. One of the difficulty I faced, when started this project, was the need of assess the island, but the information was available for each country separately, with different grade of actuality, scale, and even 2 different languages. However, I managed to make it match. In this slide, we can see the correlation between the topography and the average ISO heights. At least for the east side of the country. In the west side it's still matching, but not with the same grade. The vegetation coverage density, obtained by computation of 24 layers of satellite imagery, MODIS V6. This map also reflects a good correlation with the elevation layer and the rainfall rate. Perhaps we can see here, clearly how the western side of the island the density of vegetation falls more than a half of the east side. No matter how high those mountains are, as soon as it gets in the Haitian side, there is a notable decrease of the vegetation coverage. Bird's eye view of Gonaives, Haiti, West Coast. In this picture, can be appreciated the human-caused devastation in the vegetation of Haiti. As a consequence, the erosion has removed the major part of the original soils, so the vegetation is basically non-existing. Therefore, the evapotranspiration is negligible at most. The digital terrain model of the island of Cuba depicting the major mountain groups. Cuba have 4 major range groups, the Mayari Baracua on the northeast, the Sierra Maestra, at the southeast, the Guamuea group, at the south and center, and the Guanaguanico group, in the northwestern region. There are some other minor hilly areas, but these are the most representatives for this study. The ISO height map of Cuba with information on the average yearly rainfall. Again, we can map the highest rate of rainfall around the most elevated territory. Also, lower rates are in the areas with most intense agriculture usage. The semi-arid east region, south to the easternmost mountains, are related to the differential precipitation in the windward side than in the leeward side. This is possible here because the width of the mountain group and the strong winds coming from the windward passage. The vegetation coverage density, as shown by the MODIS V6 probe. In most of the cases, there is a good correlation between the vegetation density and the elevation. As happened with other islands, the high mountains show an index corresponding to tropical rainforest, the plains show an agricultural type of vegetation, and only in the easternmost tip, there are no match. What could be an error in the data, since that area corresponds to a different set of image cells. The Jamaica topography, depicting major features of its surface in this digital terrain model. Here we can appreciate the most important feature in this island topography, the Blue Mountains at the east, and in the central region of the island the plateaus, a high soft sloped elevation dominating the major part of the island. The rest of the topography are the coastal plains that surround the island and gets wider in the central south part of it. Map of ISO height of Jamaica, depicting the mean rainfall for 30 years period. In this map there is correlation between the rainfall rate and the topography. In the Blue Mountains only, the central plateaus do not seem to be equally correlated to the mean rainfall. Only the west part of these elevations contains significant rainfall ISO heights, that includes a flat zone on the west of the island. This case demonstrates the weakness of the adiabatic cooling tesses. This is the vegetation coverage density of Jamaica obtained from the MODIS V6 probe. Here we can observe the good distribution of the vegetation, regardless the elevation of the terrain. Jamaica has a structured and enforced environmental policy. They have the 40% of their territory taken by the tropical rainforest. The rest of the country is dedicated to agriculture and mixed uses. Excepting the area of Kingston and Montego Bay, all the rest of the territory is well cropped. There is an area at the east including great part of the Blue Mountains, where the vegetation coverage looks degraded. After inspecting the satellite images, nothing justifies these reflectance values, so we assumed it as data error. At the end of the study, we came up to the following conclusions. The Greater Antilles, besides his size or morphology, receives equally a great amount of atmospheric moisture, due to their geographical setting and the common climatic and hydrometeorological conditions. The position, elevation, and morphology of the terrains play a little role in the amount of precipitation, and the vegetation develops on it. The assumption of the adiabatic cooling as the mechanism explaining the inequity in the precipitation rate, for the same areas with different topography, is in most of the cases, non-definitory. Most of the high precipitation areas, associated with mountains are under the 3,000 meters, 700 millibars, in the tropics rarely the dew point falls under that level, as shown several SKUT reviewed for this project, goes SKUT station list. The assumption of the humid windward and dry leeward side of the mountains is limited to certain conditions, ergo, easternmost Cuba ranges, where the morphology of the terrains creates a condition for it. In the rest of the Greater Antilles the situation is not sensibly affecting the rainfall ratio. To establish a relationship between the elevation and precipitation rate, by setting a network of pluviometer with controlled altitude, in different ranges in Cuba, was unsuccessful, Hernandez et al., 2018. The major rate of rainfall, however, is registered in these mountainous terrains with the thick vegetation coverage, most of the cases, tropical rainforest. These areas have in common their lack of suitability for agriculture or urban development for its high slope rate and altitude. Only in Haiti high mountains are uncovered to the rocks, and of course it lacks precipitation. It is well known the unleashed deforestation suffered that country, through decades of mismanagement and rampant poverty. Most of the forest resources were destroyed and used as domestic fuel. It is also known that the evapotranspiration is the process of bringing a significant volume of moist into the atmosphere. Highly water vapor-loaded air masses transiting the tropical corridor of cyclone will likely reach the saturation point in those areas with a significant evapotranspiration rate. Therefore, the main and above derived conclusion is that, the main factor in the low precipitation and ultimate drought in the Greater Antilles Island is the human-driven deforestation and land use mismanagement. This is it. Thank you for watching it and please, send me your comments. Enjoy this last slide, showing a piece of the tropical rainforest of Cuba. Bye.